Hello everyone, I welcome you on Data Phoenix webinar. Today with us Nils Reimers. He is Director of Machine Learning at Cohere, and we will speak about multilingual semantic search. You can ask your question using Slander. The link is under the video. In the end of Nils' presentation, we will answer for all your questions. So for now, I give the microphone to Nils. Your stage.
Great, yeah, really happy to be here. We'll be talking about semantic search, so semantic search in general. I think it's a fascinating problem. You have like from 1,000 to 1,000,000 to 1,000,000,000 to 1,000,000,000,000 number of documents. And how can you find like within milliseconds the right relevant information? So it's like really fascinating. If you do it like on a web scale, that you're able to search over all of the internet within like 10 milliseconds and find good relevant results. So it's a really fascinating problem in NLP. And also recently with generative AI and large language models, it became really popular and we see a lot of interest in it. So it's a great technology to know about and yeah, to use it. So first, a bit about Cohere. So Cohere, what we do is we train foundation models for NLP and provide them as a service. So my colleague Phil, he's training generate models. We all know them. You give them a prompt, write me a summary about the French Revolution, and then the model writes the summary or the essay for you. In professional context, you can also use it for like other use cases like summarization, to rewrite text, or to extract information from the text. I'm in charge of the text understanding at Cohere, so my goal is not to produce new text, but to analyze text that exists. It can be like classification, for example. You have a news article. Will this news article change the credit default risk for a company? Another big use case is like search. So how can you find like big collections of data, the right relevant information for your search query? And we all have been really impressed by generative AI. But at Cohere, what we're strongly focused on is the use case in enterprises, especially large-scale enterprises. So we're not so much addressing students, helping them to write the essay about the French Revolution, but we're helping large enterprises to use generative AI in their enterprise context. And big challenge here is that generative AI doesn't know about your data. So it knows about French Revolution because it has read like 1,000,000 essays about the French Revolution. And so if you ask like to create the 1,000,001st essay about the French Revolution, it's not a problem to create this. But in enterprise settings, luckily, you don't have these homework assignments anymore, but you have like other things. For example, you want to know, you work in HR, you want to know, okay, what do our employees think about our benefits across the company? Or you work in sales, and what has this team been discussed with the client X so far? So what do you need? As a software developer, you develop some service and you ask like, hey, how can I deploy service X in our cloud? Generative AI luckily doesn't know this, so it doesn't know what your employees think about your benefits in your company. It doesn't know what you have been discussed with the client so far, and also doesn't know about your internal architecture and how you can deploy a service in it. So right now, an out-of-the-box generative AI model says, sorry, I can't help you, which is extremely limiting in usability. And so to overcome this, we're deploying text understanding together with Generate. So when you have a question like what has been discussed with the client X so far, you first search in your internal data. So you have like some customer relationship management database. You search over all the interactions. So you might have like millions, tens of millions of records in these. And then you find the respective one, like what have I declined with client X so far on the topic. You get the top 100 results, you analyze them, and then you use this as the input to the generate model and say, hey, this is like the history of the last 10 conversations, 100 conversations I had with the client so far. Please give me an overview. What have you discussed so far, and what should I prepare for the next meeting? What did I promise to follow up on? And this makes it, like, in a fully automated way, extremely helpful for in the enterprise setting, because it's no longer you need to go in, check the conversations you had with the client, which can be like really, really long, and the transcript can be really long and boring, but it's fully automated by generative AI. And to do a bit deeper dive, how does it work technically? So when you have like a prompt, like give me a bullet point list, how the headcount for the 5 biggest US tech companies changed during COVID. This is totally not a query you could give to a search system like Google. So you would only get the answer if there's like a document. So if someone did the work for you, but if you just have like the annual reports of companies, you're not able to get the information. So what we do, the first step is query generation. So from this query, we derive or search for, okay, who are like the 5 biggest US tech companies? And then for each tech companies, Facebook, Microsoft, Google, and so on, you ask, you search, okay, what is the headcount in 2019? What is the headcount in 22? You ping this to like external APIs like Google Search or Bloomberg, or you have like internal databases, for example, with analysts from your bank, with analyst opinions from your bank. You get all the results from these different sources. You put it through a stage re-rank, which is analyzing the results and say, okay, which of these results I get, which can be thousands, tens of thousands, are really relevant to write a good answer to this question. And then this goes to the generate model, and it generates you the output and cites the respective sources. And to show you how this looks like as a demo, what is this? So as a demo, how it can look like is, for example, what is the AWS free tier? So this is not using like any internal data sources. It's connected to Google Search, but obviously you can also connect it to like your internal enterprise knowledge, your code, your customer relationship information. And what the system does is, like, you say, okay, what is the AWS free tier? It searches for AWS free tier and then finds the information. So it gets like a lot of search results and then gives you an output. And what's extremely critical in the enterprise setting is that you don't produce like wrong information. So if you ask like, hey, what have we discussed with the client so far? What is the budget the client mentioned on this deal? You don't want that the model hallucinates and said, yeah, the customer is happy with the such and such price if the customer did not mention this. So critical step here is like the reference and specs. So all the outputs it's producing, you can see, okay, from which documents does it find the information? For example, the AWS free tier does not include AWS S3. And then you can go and go back. What's interesting is like follow-up questions. For example, you can ask like, how many hours can I use Linux? Here again, the first step is that query generation. So it does not only simply like for search, how many hours can I use Linux, but it knows, okay, you're in the context of AWS free tier. So I need to search for how many hours can I use Linux in the AWS free tier, and then gives you the information. The AWS free tier includes 750 hours of Linux. And similar, can I also use it for Windows? So here it's like underspecified what it is. So if I just search for like, can I also use it for Windows? The model is smart enough to search for like free tier Windows. And so you can have like a conversation with your data. So for example, let's assume you prepare some sales call. You need like a remember, catch up. Okay, what have we discussed with the customer so far? And then you can really go in and say, okay, did we present this product to the customer? What was the feedback? Is there like any other ask they did which we did not provide an answer yet to, so that you're like really well prepared for the next conversation. So my big focus here is search, and first, search has been terrible for 20 years or even longer. It simply doesn't work. So if you exclude like Google search and Bing, which is like, well, and Baidu, where you have like thousands of engineers behind it. If you search like in Word documents, in your Outlook, it's always frustrating, and it gets even worse if you're not searching only like in a single Word or PDF document, but if you need to search in like millions of documents. And it's largely addressed to like lexical search. So I'm really dislike lexical search. In lexical search, what you do is you look at all the words in a text, and then you break it down into the text, and you create a vocabulary. You say, okay, these are all the words in English. Each word gets a position in the vocabulary. So for example, the word cat goes to the first position, the word bike goes to the second position, the word cats get to the third position. And then if you search for cats, you find all documents that contain the token from the third position in the vocabulary, and you show these results to the user. The issue here is that these words have all the same distance. So the distance from cats to cat is like the same. So in terms of Hamming distance, like a 2 Hamming distance, and cat to bike is also a Hamming distance of 2. So all of these have like the same distance, but obviously it doesn't really make that much sense. So if I search for cat, there might be a relevant document that contains the word cats, which I also wanted to see. Common approach here is like more a hack. What you do is like you do stemming. So you say, okay, these suffixes, they often contribute little in English. So you take the word, and each time you would see the word cats, you replace it by the word cat. So you go in and you remove the suffix of the word. This can fail if you're searching for the company with things. If you search for the company with things, the system goes in, the stemming goes in, removes the ings at the end, and then it finds all documents containing the word with. And you're like really confused as the user. So why do I, when I search for like the company with things, find a lot of irrelevant documents about with? Second challenge are synonyms, for example, and spelling variations. So for example, we have the American English color, we have the British English color. These are like, again, for the computer, 2 different words in 2 different positions of our vocabulary. And again, it's the same distance between color, and bike. So if you search for the word color, the American English writing of color, you will not find like any documents containing the British writing of color, which is also frustrating. And you're like, okay, why do I don't find this document? I know the word color appears in it, but yeah, it's sadly spelled differently than you expected. And so a common solution in search is to use synonym list. So each time you see the word color, you replace it by the word color. Each time you see USA, you replace it by United States of America. Each time you see New York, NY, you replace it by New York. And then you create like these massively large synonym lists. Challenge, obviously, creating these synonym lists is not fun. You always miss cases. They're like embedded cases where US can either refer to like US or to us. So how do you disambiguate between these? Again, in general, it's like a really painful way to create these lists and maintain these lists. Next challenge in lexical search. Some words are quite complicated to spell. So here we have a couple who want to go on vacation. They think, okay, at this time of the year, Hawaii is nice. Let's find a hotel in Honolulu. They type in Honolulu, but sadly they misspell the word Honolulu. So they try again with Honolulu. Again, sadly misspelling, so they back off and say, okay, maybe there is no hotel in Honolulu. let's have a look at Hawaii. But again, sadly misspell Hawaii. And then they just give up, they churn, they don't purchase the product, the trip, the hotel, the flight. And yeah, instead just go to the mother in Fargo. Again, what you do in traditional lexical search is spelling correction. We all know this from Google search. Did you mean? And then gives you the right spelling for Hawaii or Honolulu. So that's like common setting. But again, how to set up the spelling correction, how to maintain it, how to add like new words to it, that can always be like a challenge. And then the final issue is that word can be ambiguous. So the word apple can either refer to like the fruit as an apple pie, or can refer to the company as an Apple store. And here the model, because both is apple, both is mapped to the same position in the vocabulary, both is like an apple, you're not able to differentiate this. And if you search for like apple pie, it might give you some results about the company, and you're wondering, okay, why does Steve Jobs show up when you search for apple pie recipes? And yeah, solution in lexical search, you just ignore it. So people did not find like a good solution for this. And this explains why search is still really terrible if you exclude like the less than a handful good search engine on the web. So if you go on Wikipedia, one of the top 10 most popular websites on earth with like millions, billions of visitors each month. And you have a really simple search query. What's the capital of the United States? Top one entry is about capital punishment in the United States because it contains the word capital several times. It contains the word united several times. It contains the word states and the and is. And so based on like the word frequency, it contains these words really often. This must be a really good search result for your search query. The correct website about Washington, D.C. is not shown on the first page or second page. So, so the user has to click through like multiple pages to finally see the website about Washington, D.C. And how can you make it worse? You can make it worse if you go like in a multilingual setup. So a lot of websites, they not only have like English users, but they have users across languages, across countries. And what you often do is like you first go in and you identify the language of the document or the query. And then if it's an English language, you use the English tokenizer. So in English, you can tokenize on white spaces. So that's quite convenient. In Chinese and Japanese, you no longer have white spaces. So you can't tokenize on this. Then you have like stemming, like removing suffixes. This works differently in English than in Spanish or Chinese. You have stop words, words you want to ignore, like is, the, which are different for every language. Synonyms are different for every language. Spelling correction is different for every language. And then for every language, you have like an independent index in your database, which you need to monitor and scale. So if you get like a lot of Spanish data in your system, you need to add like more machines and bigger machines to the Spanish index. And yeah, overall, it's like really, really brittle. And if you have to do it like for 100 languages, it's a terrible experience. And many large enterprises, sadly, they just focus on the English pipeline. So they just add like these synonym spelling corrections to English. Because the other languages in total, they are like really frequent. So in many cases, like 50% of the users are non-English speakers, but they are like too fragmented. So you have like some small population for Spanish, some small population for Chinese, some small population for German. So it's not really worth to optimize these. And so yeah, for 50% of your users, the search experience is even worse than the terrible search experience you get on English. So what's the solution to this? So it's all grounded in the issue in lexical search that the words, they all have the same distance. So the word color, colors, and bike, they all have the same distance in lexical search. They are all like one entry in the vocabulary, and the system can't differentiate, is it the word color in American English or color in British English? So this is, I think, the fundamental issue in search. And yeah, people came up with a clever idea to put words into a vector space, into a so-called semantic space, so that similar words are close in the vector space. So you have the word color, color and colors are close in the vector space. Cat, cats and kitty are close in the vector space. Cat and dog are closer in the vector space than, for example, cat and iPhone, because cat and dog, yeah, that's more similar. And an apple pie should be close to like a banana cake, and the Apple Store should be close to the iPhone. And then the idea is to use this vector space for search. So if you search for the word color, you see, okay, the closest match are documents containing the word color. Second closest is like documents containing the word color in British English, and third is like colors. And then you can do like the search based on these distances. And how well does it work? So here I also prepared a small demo. You have a query, let's search in English. How is the weather in Toronto? If you do lexical search, it will say, okay, the word weather, that's like really the important word. So it will go in Wikipedia and find like all articles about the weather. So the most relevant one is like studying how the weather works on other planets has been helpful in understanding how weather works on Earth. So this article contains the word weather really frequently. So it must matching the query, the intent from the user. And as you see with lexical search, all the results are like on the weather, and none is like really telling me how the weather in Toronto is. In contrast, if you use semantic search, first entry is about from Toronto, the city experienced 4 distinct seasons, which considerable variance in length. So the model knows, okay, if I ask like, how is the weather in Toronto? And paragraph about 4 distinct seasons in Toronto was, and then talking about the different seasons is like a really good entry for the results. And then it shows me like more information of Toronto. The model knows that Toronto is located in Ontario state. So it shows me results on Ontario state, like Ontario climate varies by season and location. And then it also finds like articles about other Canadian cities like Vancouver, Montreal, Quebec City, Winnipeg. So it's like smart enough to say, okay, which paragraphs are relevant for this search query. What's fascinating here is that it also works across languages. So I can, for example, search in Spanish. So if I say, okay, how's the weather in Toronto? And I search the Spanish Wikipedia, obviously the English search, lexical search, will not find the relevant information because it can't bridge the gap between like English and Spanish. But here again, semantic search can search across languages. So if I look at this translated, the article says Toronto winters sometimes feature short cold spells when maximum temperatures stay below -10. And it also works for really distant languages with different alphabets. So if I search for Korean, on the Korean Wikipedia, lexical search will just find articles containing some English words, like here about how kimchi tastes. If I translate, look at the semantic search results, it gives me as first result, Toronto has a cool, humid climate and exhibits typical Southern Canadian weather. And it also allows me to search across all languages. So here I just say, okay, search across all languages, and then it goes over all the Wikipedias. And here first finds the results in the Spanish Wikipedia, English Wikipedia, German Wikipedia, and then all the way down to the Korean Wikipedia. So that's like really great. If you have a data set with like many different languages. You don't know in which language is your information. You can just formulate it in like any query, be it English, be it German, be it Korean, be it Arabic. And yeah, you can use that. Building this is also kind of easy. So before, it's like a multi-team months-long effort, and now you can do like getting like an extremely good search results within like 5 minutes. So basically what you need to do is like you go sign up with Cohere. So you provide your email address, you get an API key, you select a vector database like Python, Qt, Redis, VV8, MongoDB, Elasticsearch. So there's a long list of possible vector databases. You send all your documents to our embedding API. And we'll be talking what are embeddings in a second. So you just say, okay, here's my API key, here's my list of all Wikipedia documents. You call our API, you get the embeddings back, and you put these embeddings or vectors in the vector database. And then when you search, you have the same procedure. You formulate your search query, you get the vector, the embedding back, and then you query your database for the results. And this is like all you need, like 5 minutes of work, and you get like an extremely good extremely good search system that works across 100 languages. So the idea here shown is the idea of semantic search using vectors, also called embeddings. So what you do is you project all your documents you have, like all articles, paragraphs you have from Wikipedia, into a vector space. And then when a search query comes in, like how's the weather in Toronto, this is also projected in the vector space. And then you ask the database, the vector database, please give me the top 10 closest points here. So it will return like these points because they are really, really close to the query. And this is like the results you show. And if the embedding model is good, this will be like the relevant queries, like the relevant documents that answer your query. Technically, how does it look like? What you have like some transformer network like BERT. You pass in your query or your document. You get contextualized word embeddings. So you see all the word embeddings with their distances. So the word color and colors, they are all close to each other. And then you do an average of all the words you have in your document. And this gives you a fixed size vector for the query, a fixed size vector for the document. And then you compute the similarity, for example, cosine similarity, which then tells you, okay, how close are these two vectors? So these two would be like really close. And then this is like hopefully the relevant document for your query. And the nice thing here is it's not grounded in like words you put in a vocabulary, but it's grounded in this vector space. So which make it suitable to work across languages. So if you have the English text, 2 dogs in the snow, or the German, 2 Hunde im Schnee, or the Spanish version of that, or the Chinese version of that, it's just projected into the same point in the vector space or close to the same point in the vector space. And then you find the relevant information. So it doesn't matter in like which language do you search, in which language is your information. You can just do it in one of over 100 languages, and it finds the relevant information for you, which extremely simplifies your setup. So you no longer have like all these individual components and need to think about like how does tokenization work in Chinese and Japanese and Korean and Russian and Arabic and German. How do you remove suffixes in all these languages? What are synonyms and spelling? How do you get like spelling correction in all these languages? It's as simple as shown. You get the documents, you send it to our API, you get back the vectors, you put the vectors or embeddings in a vector database, and you're done. And any improvement on this pipeline is beneficial for all hundreds of languages. So it's no longer like you say, yeah, let's make English better, but keep Spanish as is. Any improvement is beneficial like for all users on your platform. Now we're getting a bit more technical. I hope you're hooked on like that these embedding models, extremely cool, extremely helpful for search. So now the question is like, how are these trained? And the most common setup is using multiple negative ranking laws or constructive laws. Here you need some positive pairs, A for anchor and P for positive. And this can be a query and the answer, or it can be a question and some duplicate question you marked, it can be the title of a paper and the abstract of a paper, or in an e-commerce setting, can be the query and the product someone purchased. So if you search for Nike shoes, and then you purchase a certain product from Nike, this is the pair. And then what you want is that these pairs are close in the vector space. So you have like A1 and P1. They should be both close in the vector space, and all the others should be distant. So A1 and P1 should be really close in the vector space, like the query and the product you purchased. And then other products you didn't purchase should be distant in the vector space and be far away. And to give an intuitive explanation how it works, it's similar to multiple choice test, from school. So you have a question, the anchor, how many people live in Berlin? And then you have like 3 candidates, P1, P2, P3. Around 3.5 million people live in Berlin. Washington, D.C. is the capital of the US, and the 21 Olympics are held in Japan. You project all these 4 text in the vector space, in the embedding, with the embedding space. You compute the similarity between A1 and P1, P2, P3. This is, for example, 0.5, 0.3, 0.1. And then you can use cross-entropy loss, where you say, okay, this is the prediction, this is the correct answer, that the first one is correct, the other should be dissimilar, should be far away, should have like a low similarity. And then you can compute the loss and do backpropagation on that. So how did we train the multilingual model? So biggest challenge was getting data for this. So what we did is like crawl a large set of question-answer pairs from the web, remove irrelevant pairs, like a question and a cookie consent banner, or please sign up here, where the challenge is like, okay, how do you do this across 100 languages? What types of irrelevant pairs do you might get in like a lot of different languages you're not familiar with? We extend this to triplets, where we say, okay, this is a question, this is the answer, and this is like something that looks like the answer to the question, but it's like, not really the answer to the question. And then we clean the triplets, false positives, questions, and this is not the answer, or you have question, answer. And the negative is not a negative, but also like an alternative good answer to the question. And the challenges here on the scale. So at the end, we had like close to 1 billion English triplets, close to a half of billion non-English triplets. So you need like really good automated ways to look into this and clean it. It's sadly not doable by hand, especially not if you want to do this across 100 languages. The interesting aspect in a multilingual setup is language bias. So language bias means preference of certain language combinations. So if you take, for example, the LABSE model from Google, and you visualized all the English text and all the Russian text, and here there's always like one English text and one Russian text with exactly the same meaning, you see clear separation between English and Russian, which means if you search for English, the more likely returns an English document than a Russian document. And the question is language bias good or bad? So side effect with language bias, same language results are ranked higher just because of the language. And there might be better hits answers in other languages. So if I ask like, how is the weather in Toronto? If the model has language bias, it would first get the English paragraph from the English Wikipedia. Even such in other languages, there might be like more information, better information on how the weather in Toronto is. You could argue for language bias on the one side, user preference. If I search in English or if I search in German, I might prefer reading a German paragraph than like a Korean paragraph. And also in terms of confidence by the model, so it's easier to compare like a query document in the same language for relevance than to compare this across languages. So you could argue you want a model without language bias, but this also has side effects. So if you search for the word wedding and you search for images, so with images, you can use the same semantic search approach. You project text and images to a vector space and you search for wedding, you might get a picture like this. So the man, a white man in a black dress, the white woman in a white dress, smiling each other, celebrating. If you now search in Hindi for the word wedding, the model doesn't know that the input is like Hindi. So it just knows, okay, the input is like wedding, and it will find a picture like this. But you could argue if someone searches in Hindi, which is dominantly spoken in India, they might want to get like a picture of like an Indian wedding and not of like a European, North American, white people type of wedding. But again, the model is not aware of this, so it's not able to differentiate between these. Same if you say, who's the president? You might want to get the answer, Joe Biden is the president. If you ask this in French, if the model doesn't know that it's French, it will give the answer, Joe Biden is the current president. So here, the problem is that we lose a lot of information, context information, based on the language. Where is this person likely from? And what type of information does the person want to see? Now I want to come to some challenges in semantic search. So if you use it correctly, it works really well, but there's still sadly a lot of challenges where it breaks. One issue is like multiple topics. So if you have a text like bananas are the most sold fruit, you project it in the vector space like this. If you have a text like Facebook was founded by Mark Zuckerberg, it's projected in the vector space like this. And now you have a text, bananas are the most sold fruit. Facebook was founded by Mark Zuckerberg. Question is like, where should you put this text? Should you put it, the vector, like close to the bananas? Then it's just found if you have questions on bananas. If you put it here close to Facebook, it just found if you search for like the founder of Facebook. Or should you put it somewhere in between? But the challenge is like, what's in between? Is it like already filled? Maybe there's like some content already there. So the space is already taken. And this can lead to like really strange results. So for example, in e-commerce, assume you have jeans in a certain size that has like different colors, like yellow, pink, blue, red, and so on. And if you search for like blue jeans, you see the second entry has the jeans available in green, yellow, or orange, or in the next one is like black, pink, or red. So the issue is here that the average of like green, yellow, and orange is really close to the word blue. Same for black, pink, and red. This is also really close to the position of blue in the vector space. And hence you get like these really strange results where you search for blue jeans and yeah, half of the top entries are jeans, but not in blue. And then also like jeans that are available in blue are like significantly ranked lower. Further challenges like multiple fields. Let's say in e-commerce again, you have a product image like this, you have some text, some product title like this. And if you search for like red Levis jeans, it's really hard to answer this. So if you embed the text into the vector space, you know, okay, this is a Levis jeans, but you don't know the color. If you encode the image in the vector space, you know, okay, there's a jeans, but also like a top and a necklace in it. But you don't know that this is like a Levis jeans. And how can you now get the information from the image as well as the text? So currently this doesn't work. Next challenge is long documents. On the one, so typically what people have, it's not like these short paragraphs, but they have like a long document, like an annual report. Here, an annual report from Johnson & Johnson, 140 pages. On the one side, you have the context length limits of transformers. Now we're making good progress to increase the context length limits of transformers. But even if we solve this, we have the challenge that one embedding can only encode like one topic. And if you have 140 pages, there are like so many topics covered in this annual report, it doesn't make sense to put this into like a single embedding. And then you run into the challenge like 140 pages. How many topics are there? How do you chunk it down, break it down? So most common approach is to chunk it either on like paragraph level or to have like fixed sized window where you say, okay, I always take 100 words and embed these. But here you run into like a lot of information on missing context, which is suboptimal. Finally, semantic search just looks on the text level. So if you search for updates on AI, you have two podcasts. One is the AI update, the other is like last week in AI. The AI update is a better semantic match to updates on AI than last week in AI. So you would show this podcast higher than this podcast. However, when we're browsing for podcast and other things, we're not only interested in like how close is the match on a textual match, but there's also, so for example, some release information, there's a rating. And if we see AI update was released in May 2015, got a 1 out of 5 star rating from users, but last week in AI was like released in July, got 4 out of 5 stars. You, as a user, would prefer probably this. So you want to have this higher ranked in the search results than this. And so right now there's like no way, no approaches. How can you encode like release like recency of information? How can you encode popularity, star rating of content? So you just stick with the text match and can't take like these relevant information into account in a semantic search space. As conclusion for today, semantic search is amazing for multilingual setups. So as mentioned, same pipeline for all languages. Within 5 minutes, you're good to go. It works amazingly well. And if your data can be represented as short paragraphs, so that's a big limitation, short paragraphs that cover one topic. If you have longer documents, multiple fields, multiple topics, and other ranking signals like popularity, recency, rating, semantic search has a lot of issues in here, and you need like a lot of like work hacks to make it solve. Like for what people often do is like combine different things. So for example, you search on embeddings, you take the similarity on the text level, and then you add like, say, okay, we match or rank 80% on the similarity of the embeddings, 10% on the recency, and 10% on the rating. And then you hope that you get the right content on the first position. But this also works, such and such. Currently at Cohere, we're training a new foundation models for search, which will work amazingly well. So the first internal demos are really cool, which solve like all the previous mentioned issues. And give you like really good search results on like arbitrarily complex documents, which is like, really, really cool if you want to go out of from a demo to like a really production use case. So in a demo, you often can cherry pick data sets or queries where it works. But if you put it into production, you see, okay, there's like a lot of really complicated queries. So if you search on like your CRM data, you get like really complex queries in this case, where so far current solutions are not able to do this. But we're currently training a new model in this direction, and really, looking forward to really research this model and talk more about that model. Great. That's so much from my side. Looking forward to any questions you might have.
Yeah, thank you for this presentation. Interesting presentation. Yeah, we have some questions. Let's try to watch to it and to answer. Just about how long should the model be for high performance embedding models? How large should be this?
Yeah. So the larger models, they don't produce better embedding. So luckily, we don't need 100 billion of parameters for this. It's like basically zero or little improvement on that. So maybe it gets better results on 1 out of 1,000 search queries. but it's not really worth the price and effort to get like this one improvement on 1,000 search queries. So a really good model size is something between like BERT base and BERT large, like 100 to like 350 million parameters. Beyond that, it's not that relevant. So what's more critical is the training data you have and the way how you train it.
Good. Yeah, we will publish the recording of this webinar, so not forget to subscribe to our YouTube channel, and you will get the recording of the webinar. Next question about search of a lot of documents, for example, 3 million. Search should be fast.
So this is the part of the vector database. So you can do it on like billions of documents within like 5 milliseconds. So it's really fast. What they use is like so-called proximate nearest neighbor. So they don't compare the search query to like a billion other documents. But you create an index, like an index in a database. So there are like specialized indices for vectors that allow like a really quick lookup, and then say, okay, within a few milliseconds, you can say, for this query, these are the 10 closest documents, and then you can return this. Okay, so next question is about the score from vector similarity. Is it calculated confidence score? Yeah, this is sadly a really common misperception where people compute the similarity, use it as a confidence score, do some thresholds, and say, okay, I only show results that have higher than 70% cosine similarity. It's sadly not a confidence score. It's sadly really hard to interpret. So for example, we had like one use case. It was in the beauty domain. We wanted to know like how many YouTube videos are published on certain topics. And there we were using semantic search. When you were searching for like lipstick, it found like, I don't know, 1,000 videos. If you say, okay, how many videos were published on red lipsticks, it found 5,000 videos. So which doesn't make sense. So obviously there are like more videos on lipsticks than on red lipsticks. So yeah, using this threshold is sadly not possible. You need to design your app, your application to not use the threshold, or to find like other ways to get around. But yeah, that's also like a problem in semantic search that's like really hard to say, is a document relevant or not? Should I show it? When should I show? I did not find like results on this. It's an open problem in the search community for the past 50 years. So yeah, so right now, yeah, do it on the UI design, and maybe eventually research community will find a solution for that.
Yeah, next question about some results. Something what we don't want to find.
Yes, so in the blue jeans example, so one approach which works nice is our re-rank endpoint, which you can check out. So it uses slightly different technology. It's a lot more powerful, which does like a sanity check. So what's really good, like you do semantic search to get like top 100 candidates, and then you pass this over to re-rank, and then it will remove like all the genes that are not blue. So here it returns like a score for every entry. It's a bit easier to interpret, but still in general like kind of like a challenge to say what do you want to show. Also from the user experience, if I search for like blue jeans and there's like no blue jeans available in my store, should I say sorry, I did not find anything, or should I show like alternative jeans like green genes or bluish genes. So here's then really the hard to make boundary, like, okay, where do you make the cutoff?
Yeah, thanks for answers. Are there any other calculations biased consistently similar that can be used to calculate embedding?
Yeah, so there's also dot product. In a research paper, in the beer benchmark, we talk more about cosine similarity versus dot product. Cosine similarity, which is the most commonly used metric, has a lot of issues where it finds like irrelevant documents. It finds like really short documents that all look like a paraphrase of your query, which is like not really the answer to your question. And hence, our most recent multilingual model is using dot product, as it's giving you better results because there it can take the magnitude into the account. So in the magnitude, you can encode how much information does an article provide on a topic. So not only like, is it on the topic, but also how much information is it? So it can show results that contain more information, like how is the weather in Toronto. It can show you the paragraph, the article with more information on this topic over a paragraph that just says the weather in Toronto is great. So final question is like synonyms of vitamin C. How can we train embedding in order to find all possible synonyms of vitamin C? So with vitamin C, luckily, it's easy because it's a really common, well-known concept. So in the pre-training of the model, it's like has been trained on all of the internet. So it has seen a lot of examples of alternative names for vitamin C. So that's not the big challenge. Challenge is more in like these domain specific setting where like in your enterprise, you have like a lot of synonyms, let's say for the same service. Let's say you have like 10 different names for it. And the model doesn't know this out of the box. What's required here is to either have like training data, that you provide like a lot of training data to these models, that you so you get like all possible text you have and a lot of search queries you have, and then the model will eventually learn it. But this is also not really feasible in many enterprise settings, because it's often you don't have that much data that talk about synonyms of a certain product you have. So here you need to find more data efficient approaches. Our re-rank approach, for example, is a lot more data efficient. We can find a lot more of these synonyms. You could define like synonym lists where you add this as additional information and say, okay, vitamin C, here are like 10 alternative names for vitamin C. And then the model can take this into consideration. So if it sees a document talking about ascorbine, it knows, okay, this is a synonym about vitamin C. But here you're sadly again back to like synonym lists, which are a bit unfavorable. So in the best case, my goal is to have like these self-learning systems where people search, you click on data, you interact with the system, and based on these interaction, it learns the synonyms for vitamin C or for your product, and then it can incorporate this knowledge in the model. But yeah, that's still future stuff where we have a lot of things to do to enable this.
Yeah. Thank you for your answers, for this good presentation. I hope it was useful for all who watch us today and will watch the recording. Thank you.
Great. Yeah. And yeah, check out Cohere or embedding model if you work on like multilingual data. It's really cool. And yeah, build nice applications on that.